27 minutes. All right, greetings, YouTube. Beautiful mind here. So this next series, we have a series of 8 questions from calculus. These are mostly calculations, so should go a little bit faster and more smooth or smoother. This first question of 8, it asks us to use the midpoint rule with the given value of n to approximate the integral. Round the answer to 4 decimal places. So the midpoint rule it's an approximation technique for finding the integral of a curve, and the integral is basically giving us the area under the curve, and the integral also is basically like the reverse of the derivative. So how we've been taking the derivative the whole time, like how we were given a function, we take the derivative, we get an answer. So the integral, we start with the answer, and it's a method for us to work backwards. It's like the reverse of the derivative to get back to the original. And so we introduce the integral with this like Riemann sum. So like if we have a curve, and we consider the curve as x goes from like one number to another, and we're going to break that interval from x from a to b, we're going to break it up into subintervals. And so each subinterval is going to have a different height based on where it touches the curve. And then, so the sum of those smaller subintervals is approximately equal to the area under the curve. And the smaller those subintervals are, the better our approximation. So in this example, we have some curve. We're going to pretend like we don't know what it looks like, because we really don't without a calculator or something like that. But we're going to consider this, whatever curve this is x goes from 1 to 3. We're going to break that interval as x goes from 1 to 3 up into five equal length subintervals. We're going to find the corresponding y for the midpoint of each subinterval, where it crosses the curve, and then we're going to find the area of each of those curves, okay? I know that's a mouthful. Conceptually, it's not as bad as it sounds. So if we're working with that function, right, let's I think some graph paper is probably a good idea here. Okay, let's try it again. Okay, so let's just start with the x-axis. So we'll start with like positive x over in this direction. Okay, and we want to consider this as x goes from 1 to 3. Okay, so let me see. I'll let this be my 1, 2, 3, and I'll go a little bit beyond. Okay, so like for instance, again, if this is my origin over here, this is when x is 1, when x is 2, when x is 3, when x is 4. So then what we want to do is break the interval from 1 to 3 up into 5 equal subintervals. So then 2 divided by 5 is 2/5, right? Let me see how we can get that. Four out of 10. Okay, so 2/5. It's a little bit weird. Let me think. What's it as a decimal, right? 2 divided by 5. Let's do 2 divided by 5. Yada, yada, yada. It's 0.4. Okay, let me think. So that's 0.5 and that's 0.25. It's a little bit off, but like, okay, I'm just going to use my decimals. So this is going to be 0.4, right? We want 0.4 there. And then we want 0.8. Okay, so if we want every fourth, let me redraw this. Let me think about this, because we want like powers of 4. Okay, I think I got an idea. Let me kind of start over. And we basically want multiples of 4, right? So say this is my origin. 4. If I go by 2's, 2, 4, 6, 8, 10. That's kind of far. Okay. So then if I go 2, 4, 6, 8, that's my 1. 2, 4, 6, 8, that's my 2. 2, 4, 6, 8, that's my 3. 2, 4, 6, 8, and that's 4 over there. Okay, so now we got something we can work with. So say this is my positive x here. 2, 4, 6, 8, that's my 1. 2, 4, 6, 8, that's my 2. 2, 4, 6, 8, that's my 3. 2, 4, 6, 8, my 4 is here. Okay, my origin is here. So that's my x-axis, right? So now we have tick marks that we can use. We're going from 1 to 3, where each subinterval has a width of 2 over 5, which is 0.4, right? So 2, 4. So this first one should be like 1.4. I'm just going to label it, I guess. We'll go blue. So that's like 1.4 is the first one. And then what, 1.8? And then what, 2.2? 2.6? And then 3. 3 is the last one, right? So on the x-axis, we have those subintervals. So then what we want to do is find the corresponding y for each subinterval, but we're going to do it based on the midpoint, right? The midpoint formula, so we're going to use halfway between each subinterval. So the first subinterval runs from 1 to 1.4. Halfway will be 1.2. So when x is 1.2, we want to find the corresponding y. Okay? So to do that, I'll just close these out. Okay. Okay. So I'm going to go to my y equals, let me see, we got x divided by x squared plus 7. Okay. Go back home. I want to evaluate this function when x is 1.2 is my first subinterval. Okay. So then the corresponding y, can we get something cleaner? Let me see if I hit math as a fraction. Okay. So we get 0.1422. 14. Let me see the next one. So when x is 1.8. 14, okay, 7, so 17.17. Let me look at 2.2, when x is 2.2. Still 0.18. Let me go ahead and look at 2.6. So 0.18, and let me look at when x is 3. Oops, 3. So 0.18, so it looks like it went from like 0.16 to 0.18. I'm thinking let the y go up to like 0.2, right? And just think of like as if you were going to 20. Let me see. If this was like my 2, let me get rid of this. So let me see if this was my 2, 4, 6, 8, 10, 12, 14, 16. Let's try that again. We're trying to get to 20. What if we went 5, 10, 15, 20? See, that's kind of jammed. What if we went by 4s? 4, 8, 12, 16, 20. Okay, so we want it to go to 0.2. So then this would be what? 0.04, and then 0.08, and then 0.12, and then what is that? 0.16, and then 0.2. Okay, so we'll let this be our positive y in this direction. Okay, and you know each of these tick marks is essentially 2, 4, 6, 8. Yeah, 0.02, right, up to like 20. We don't need that 0. Okay. All right. So let's go back. When x was 1.4, I guess we can work backwards since we got this. So when x was 3, the corresponding y was 1875. When x is 3, and let me change this. I do better with this. Come on. Okay. So when x is 3, the corresponding y, 1875. So let me see. 0.2 halfway is 18, so almost 19, so about there. And we're going to label it, that's the ordered pair, 3, 0.1875. Right, that's the corresponding y. We're going to use that in just a moment. Okay. And then when x was 2.6, it was a little bit higher, 1890. So this one, 1890, almost 19. So that was 2.6, 1890 is what we got. Okay. Let me see. Yeah. Probably might be better off writing out that long decimal, 1889.53, or write it out a few more digits. Idealistically, you don't want to round it to the end. The earlier we start rounding, the more skewed our final answer, the more off our final answer will be. 89.53, right here. 89.53, 48.84. 48.84, right? So along the way, if we're not going to have an exact result, it's best to write out the long decimal and only round at the very end. Otherwise, it's going to be more challenging to get the correct answer. But I'm probably still going to round. 1858. So this point, 1858, so it's lower. 1858 is here. That was 2.4. 1858. That's 2.2. 1858. 108108. 108108. Okay, let me change that 4 to a 2. Okay, we probably could put this in the table, but let me just kind of go with this for now. Okay, let's look at 1.8. We need 1, 1.4, and 1.8. So let's go ahead and do our 1. Or let's be consistent. Let's go ahead and do our 1.8 since we've been working backwards. 1757. 1757. 16, 18, 1757 is about here. And that was 1.8. 1757, 8125. 1757, 8125. Okay. And we're gonna let's just try to get the last couple. 1.4. 1562.5, 1562.5, 12, 14, 16. It's about here. That one, 1562.5. And then the last is when x is 1. Okay. 125. Right here, that's 12, that's 14, 13, so about there. Okay. All right. So again, we found these corresponding y values. Now I probably could have put them on the far left, but we found these corresponding y values based on the midpoint of each subinterval, right? So then the way we kind of bring this together, let's go like this. Let's go this color. So this first subinterval is like here. Let me go style, stroke, like this, fill, like that. Then I want to duplicate. Oh, wait a minute. Oh, shoot. I didn't do something right. I need to back up. Let me delete. So, yeah, I didn't do these right. Okay, let me go back. I used the wrong numbers. I just realized I used the wrong numbers. Let me back up. Delete. Undo. Let's go. Trying to get rid of this stuff. Delete. Okay. I forgot I was supposed to use my midpoints. I used my endpoints. But I think a table might be easier instead of, let's do a table real quick. So again, if we're going to do it based on our midpoints, the midpoints, and we're doing 5 subintervals, that means we're going to do what? Our x versus our, I guess you could say f of x. We're going to do what? 1.2, add 4, so then it's 1.6, 2, 2.4, and then 2.8. These are the x values I need to do. So honestly, I can make a table in the calculator. So if I go to like table set, I want the table to start. We'll have the table start at 1.2. We wanted to change by 0.4. And then my table's the top right, so I'm gonna hit second graph to access the table. So then these are rounded, but I think we can use them. So then the corresponding y, when x is 1.2, looks like we get a 1.14218, 1.6, 1673.6, 1673.6. When it's 2, 18.182, 18.182. When it's 2.4, 18.809. Okay, and then 2.8, 18.868. Okay, so we have our x's from the midpoint of each subinterval with the corresponding y. Okay, so then I'll do a quick plot. Let me see, 14.21.8. So 1.2, 14. Halfway will be 14, 15. So the first one is about here. Oh. Okay, that's the first subinterval. And then when x is what, 1.6, we got 16,736. 16, so if that's 16, that's 18, 17, so 16,736 is about there. Next one is 2, and then 18,182. 18, so that's 16, that's 18, 19, so right about there. Okay. 2.4, 18,809. 2.4, 18,809, so that's 18, back up, 16, 18, 19, 809 is about there. That's fine. 18,868 for 2.8. Right here. So that's 16, that's 18, that's 19. No, that's 20, that's 18. So right about there. Okay. Okay. So again, now let's make our boxes. We can just go like this. Duplicate. 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 It's kind of struggling because it's trying to snap to the grid, so it's giving me a hard time. Okay, so the height of each of these subintervals was based on the midpoint, and I'm going to do this real quick. Okay. Style, stroke is thin. That's fine, and the fill is blue. That looks good. Let's duplicate. Okay, and duplicate. So this graph or image is just a pictorial representation of what we mean by like Riemann sums with this like midpoint rule. So again, we're considering. So again, we don't have the curve and we don't really need it. But what this part in blue represents is an approximation of the area under the curve, right? So we consider the curve as x goes from 1 to 3. We broke the subinterval from 1 to 3 up into 5 equal parts. So then we had to do steps of like 0.4. It ended up being 2 over 5, which was 0.4. So you saw how we constructed that so that we can get those subintervals correct. And then we found the height of each subinterval based on the midpoint. So for instance, halfway between 1 and 1.4 is 1.2. So when x was 1.2, the corresponding y was 14, that point 14.218, yada, 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 right? Those corresponding y's came from the midpoint of each subinterval. Okay, so then if we want to approximate the area under the curve, again, the curve would pass through those blue dots at the top. So then we just basically find the area of each rectangle and add up the areas. Area of a rectangle is what? Length times the width. The width of each rectangle is 0.4. So we're going to say 0.4 times each of those heights, add up our answers, right? So long story short, we're going to say this time, this, I'll do it in purple, times 0.4 plus this times 0.4 plus this times 0.4 plus this times 0.4 plus this times 0.4, and we're going to get some answer at the end. Okay, so that's essentially what we're doing. Length times width plus the next length times width. They all have the same width, and they all have different lengths. So then that's essentially what we're doing. Okay, so the way I'm going to do that to be a little bit more precise in my calculations, instead of using those, because if I use those rounded results, it'll kind of skew my final answer. What I'll do is I'll say like, you can honestly factor out that 0.4. You could just do the summation, right? Instead of saying, f of 1.2 times 0.4 plus f of 1.6 times 0.4, you could say, you can do the sum as n goes from, let me think. You could do a summation. Let me think about it for a second. N goes from 1 to 5. I just got to think of the proper construction. I think I am just going to do my f, right? So I'll call in the function that I typed in. I want to evaluate this function when x is 1.2. Whatever answer I get, I want to say times 0.4. That's going to give me the area of that first rectangle. The y times the length, the height times the length. Then I'm going to say plus, I want to evaluate this function when x is 1.6 times 0.4. Now I can just do the 0.4 at the end. If I factor it out, instead of doing times 0.4 every time, I can do parentheses. Let's do 0.4 times parentheses. Now you would just say the sum. Anyway, I'll just do it manually because I just don't feel like figuring out the summation notation. When x is, the first one was what, 1.2 plus when x is 1.6 plus the function when x is 2 plus the function evaluated when x should be 2.4. Okay. Last one plus when this function is 2.8. Okay. Close off my parentheses. So again, essentially what I did, let me just. So again, I'm basically finding the area of each rectangle. The width of every rectangle is 0.4. This first height is that 1421.8. So instead of doing the 1421.8, I did f of 1.2 to get me this corresponding y here, right? So this is f of 1.2 times the 0.4. So I factored out the 0.4 and I did it in this form. You could do a summation to get it all in one go. I just didn't feel like thinking about that. This is something that I could see. Let me try to wrap this up. So if I hit enter, so our claim is that the area under the curve is approximately that. Okay. So then we get that this is approximately, it's at 4 decimal places, so that would be 3473. Now what we can do is actually find the integral and evaluate it, and we should get something close. If we get something close, then we can be kind of confident. So what I'm going to do, I'm going to go to my math, go to the very bottom by hitting up. I think it's the f integer, number 9. I want to take the integral of our function with regards to x as x goes from 1 to 3. 1, 3. It might give me an error because I may have typed it in wrong, but let's just give it a go. See if we get something similar. Yes. Okay. We got 73. They got 66. You know. It is close. Now it's just a matter of will the book accept the 3473, right? But that's the idea behind the Riemann sums. Again, this technique is an approximation. It's not as precise as actually finding the integral. The only difference is with the integral, you see how the width of each subinterval here is 0.4? Well, what if we did, instead of doing a subinterval of 5, what if we did a subinterval of 10, or a subinterval of 100, or a subinterval of 1,000, right? So the integral is take the limit as those subintervals go to infinity. And that's what the integral is. So the integral is going to be the best approximation we have for the area under the curve. But for this purposes, I'm pretty confident in that 3473 at the top of the screen. Okay. I know there's a little adventure. I did have to kind of like remember some aspects of it, and I did make that mistake that ate up some time. Again, this technique is really just for like conceptual purposes, just to understand the concept behind the integral. It's not really practical. We wouldn't really use it. It's really just to introduce the concept. We have more sophisticated techniques for finding the integral. Okay, so thanks for going on that little adventure with me. Hopefully, the other ones go a little bit more smoothly. Okay, so again, that was question 1 of 8. And we will be back momentarily for the remaining portions. All right, see you in just a moment. And we're back. Greetings, YouTube. Beautiful mind here. This is question 2 of a series of 8 from calculus. This question asks us to use the midpoint rule with the given value of n to approximate the integral. Round the answer to 4 decimal places. We have the integral as x goes from 0 to pi of 3x times sine squared x dx with 4 subintervals. So 0 to pi over 2. So we just need 4. Okay. So let's start with some graph paper. And we want to, let's see, we need at least 4 tick marks on the horizontal axis. So say like this is our origin. There's a 1, 2, 3, And 4 is there. Okay. So we'll let this be our positive x in this direction. We'll come back and do some tick marks for y in just a moment. Okay. So if we're going from 0 to pi, 1, 2, 3, so we want this to be pi. We want 4 subintervals, so then this here needs to be what, pi over 2. This needs to be what, pi over 4. Midpoint rule, that's fine. How do I want to write this? I'm gonna, let me see. So it's basically 8, right? I'm gonna change it up a bit. I mean, this is fine. 3 pi over 4, right? 1, 2, 3, 4. Okay. One, 2, 3, 4. Okay. So I'm gonna go ahead and label these guys as well. This is a pi over 8 here. 1, 2. This is 3 pi over 8. 3, 4. This is 5 pi over 8. 6, 7 pi over 8. Okay. Okay. So then the half, if we're using the midpoint rule, the halfway is like the pi over 8. So let's do our table. I felt like the table was a lot more smooth. So we have our, we'll just say x versus our f of x. Okay. And so if we're using the midpoint of each subinterval, the first midpoint is what? Pi over 8. The next midpoint is 3 pi over 8. The next one is 5 pi over 8. And the last one is 7 pi over 8. Okay, those are the midpoints of each subinterval. So then we need to find the corresponding y. So I'm going to just do my table like I did last time. Okay, I'm going to go to my y equals and clear. We got 3x. This needs to be in radians. Okay, I think we're good there. So then 3x times the sine of x quantity squared. I think that should work. Okay. Then I'm going to go to table. I want my table to start. We can have it start at pi over 8. And we wanted to change, let me see, what is that? By 2 pi over 8 or pi over 4. I'm just going to have it change by 2 pi over 8, which is essentially pi over 4. Okay. All right. And then if I go to my table, now it's not going to show. We do need to probably confirm those numbers are correct. Let me see, but it should be the first 4. Okay. So what we can do, did I hit something? Pi over 8, I think it's this one, right? Okay. Everything is just flying. 17,253. Maybe we can get an exact result here. 3 pi over 8. Let me see. Pi over 8. Pi over 2. Sine of 90 is a 1. Pi over 8. I guess I'll just use my decimal approximations. 17,253. 17,253. 167. 278. 2077. Wait a minute, I guess so. 2077. Now, as far as these other decimals, we got 7489. I just want to confirm that these are correct. 9635. 1781, 3927. Okay, so let me just make sure this is proper. I want to evaluate the function. Actually, let's just do pi over 8. We should get that decimal. 3927 is good. 3 pi over 8. We should get 1781 is good. Yada, yada, yada. I'm going to just trust that that's good. Okay. So I have my approximations. So I didn't find the exact, but we can still use this. So maybe we need to go up to like about 5 on the y-axis. I mean, we don't really need to draw the boxes. We just need to basically say the width of each box, which is going to be what, pi over 4, times these y values. All right. So what I'm going to do, I'm basically saying pi over 4 times f of pi over 8 plus f of 3 pi over 8 plus f of 5 pi over 8. This is what I'm going to put in the calculator. Plus f of 7 pi over 8. That's what I'm putting in the calculator. And we'll use that to get our approximation. Okay. Zoom out just a little bit. Okay. That's clear. We got our pi over 4 times. We want to evaluate the function when x is pi over 8. Okay. Plus evaluate the function when x is 3 pi over 8. Okay. Plus evaluate the function when x is 5 pi over 8. So then hopefully my keystrokes are good. Plus evaluate the function when x is 7 pi over 8. Okay. Close off my main set of parentheses. Cross our fingers. Let me, this should be okay, but I'm going to insert some parentheses up here as well, just to be on the safe side. Okay, so then we get an approximation of 4 decimal places, 4022. Again, we could calculate the exact, but for these purposes, I mean, something like this should suffice. Okay, so yeah, that was much smoother and faster. All right, we didn't. I just bypassed drawing the squares. You don't really need it. You just needed. You gotta, as long as you understand the concept that we're finding rectangles, and we're finding the area of each rectangle. So we're saying the length times the width, or the height times the width, right? The height we're generating from the midpoint of each rectangle. They should all have a width of pi over 4. So then we're just saying pi over 4 times each height, adding those results up. This one we got approximately 7.4022. So just try it. Let me know how it works out for you. And with that, we'll go ahead and close out this question number 2, and we'll be back momentarily for the third installment. Take care. From one beautiful mind to another. See you in just a moment. All right, and we're back. Greetings, YouTube. Beautiful Mind here. This is the third installment of a series of 8 questions from calculus. These questions have been centered around finding the integral. This one asks us to express the integral as a limit. This was to be. I gotta edit that. Come on, that's auto correcting. It's supposed to be Riemann sums. Let's see. Okay. Hopefully that'll be minimal edits like that. Express the integral as a limit of Riemann sums using right endpoints. Do not evaluate the limit. Okay. So this is kind of broken in parts for us. The first part asks us to find the width of each subinterval in terms of n. So in the previous couple of questions, when we found the subintervals, it's like the first one I think said 5 of subintervals as x went from whatever it was, 1 to 3, right? So we said 3 minus 1 divided by 5. So it ended up being 2 over 5. So the width of each subinterval was 2 over 5 or 0.4. For the second one, it was the use the midpoint rule for 4 subintervals as x went from 0 to pi. Right? So we said pi minus 0 divided by 4 because we had 4 subintervals. So the width of each subinterval ended up being pi over 4. So here, if we're going to evaluate this as x goes from 3 to 5, we would say 5 minus 3 divided by n. So it's going to be, the width of each subinterval is going to be 2 over n. The width of each subinterval is going to be 2 over n. Okay, I'll do my answers in purple so they pop a little bit. So then it should be 2 divided by n units. Okay, for that first part. Find the ith endpoint in terms of n. Okay, so using the right endpoint, right? We want the right endpoint. So if we started with 3, say we broke this into like 5 subintervals, right? So then the first subinterval, x sub I or x sub 1, would be 3 plus 2 over n times 1, right? So for n were 5, we would say 3 plus 0.4, right? And then the next one, we would have to say 2 times, right? All right. So long story short, if we want the ith endpoint in terms of n, that's going to show up as 3 plus 2 over n times I, right? So like if we, like the first subinterval, right? If we wanted 5 subintervals, our n would be 5. So then that first right endpoint would be 3 plus 2 over 5 times 1. The second right endpoint would be 3 plus 2 over 5 times 2, right? Because we want to double up the width. Then we want to triple and whatever n is. The ith endpoint in terms of n, right? I feel like there might be some more. Find the ith endpoint in terms of n. Okay, I think I need to adjust it here. Let me think. So that first subinterval, right? I feel like this is what it should be. This one, I don't know. They might want it to look a little different. I might need to make an adjustment. Let me think about it just for a moment longer. The second subinterval, 2 times that. I'm going to go with this. It might not accept this. Again, this is just, I don't know why they're doing it, like being extra like this. Like this is like trying to introduce the concept and trying to get you to think about it a little bit differently. Again, you know, we're not really going to do it like this. This is just like for introductory purposes. Like you can just do your best with this, but you can bypass this and be okay. Like just do the best you can with this. Again, if it's not right, just let me know and I'll come back and revise it like we've done others. Okay. And then we're asked to evaluate the square root of 5 plus x squared at the ith endpoint. Okay. So then f of x sub I, so then we would just take this result and plug it into that square root. Evaluate this at the ith endpoint. It needs to be I in terms of n. Because the width of each subinterval is 2 over n. And then that says I goes from like 1 to n, right? Yeah. So then I'm not gonna like expand it, but if we did f of x sub I, then that would be what? The square root of 5 plus this 3 plus 2 over n times I, quantity squared. All right, I'll just leave it like that. Okay. Again, it may or may not take this, so maybe I'll check another source before, I release all this. Express the integral as the limit of Riemann sums using right endpoint. So as x goes to, the limit as x goes to infinity, so that's off to the far right, as I goes from 1 to n. Okay. That's in subintervals. X goes off to the far right. I feel like I'm missing something there. Let me see. Okay, I think I might look this one up. Let me think about it for a second. Okay. Let me pause this. I might just redo this one. We'll see. Okay, so we're back after a brief pause. I was debating as to whether I was going to restart this one or not. I think I'm going to keep what I have because we're actually not that far off. But I'll do a quick recap. So express the integral, yada, yada, yada. Find the width of each subinterval, right? So we're going from, as x goes from 3 to 5, that was fine. So we would say 5 minus 3 divided by n, so that's 2 over n. So the width of each subinterval, that's like our delta. That's also, you can also consider that our delta x. The change in each x, right? So we can use that later. Find the ith endpoint in terms of n. So if we're starting at 3 and we're going up, like the first one, we go up a distance of 2 over n. The next one, or 3 plus 1 times 2 over n. The next one is going to be 3 plus 2 times 2 over n. The next one is 3 plus 3 times 3 over n, right? That's the ith endpoint in terms of n, right? That's fine. Let me check here real quick. Let me see. Yeah, I think we're good. Yeah, let's keep going, right? So then evaluate this at the ith endpoint. So, I think that's fine. That's, so f of xi is there. So then to express the integral as the limit of Riemann sums, I feel like there should be an a there, but that's fine. We're good. Okay. So basically what this part is your f of xi times delta x, right? F of xi is there. Each delta x is 2 over n. So if we put those two together, we would say the only part we were missing was this 2 over n times the f of xi, which is the square root 5 plus 3 plus 2i over n, quantity squared, like that. All right. So again, that last part, all we did was f of xi times delta x. You can see delta x at the top of the screen, which is that 2 over n. Each f of xi, you see at the bottom, 5, yada, 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 based on whatever your I is. And so basically, yeah, you just put those two together. Okay? And I think that was the end of that one. So we weren't far off. We just had a little bit more that we needed to do. Okay? And so with that, we're going to end this session here, and we'll be back momentarily. Let's at least get the whole image. So that concludes the third installment. And I think they get a little bit lighter. I haven't really worked them. I usually work these on the fly. Like I said, with this one, I did get a little stuck, but I feel confident in these. Again, if it's not right, just let me know, and we'll come back and try to break it down. All right, so we'll go ahead and close out this third installment, and we'll be back momentarily for the next installment. And from one beautiful mind to another, take care. See you in just a moment. Peace. All right, greetings, YouTube. Beautiful mind here, and we are back for the fourth installment of the series of 8 questions from calculus. This question asks us to use the form of the definition of the integral given in this theorem. I'm not really sure what theorem it is because it's a link that I don't have access to right now. To evaluate the integral, we got the integral as x goes from 0 to 2 of 5x dx. Find the width of each subinterval in terms of n. So this one is similar. At least it starts out similar to question 3 that we just did a moment ago. Let me see. Width of each subinterval in terms of n. So we would say what? 2 minus 0 divided by n. So the width of each subinterval should be 2 over n units. Okay. Find the ith endpoint in terms of n. So the first, and I guess we're doing the right. It doesn't tell. So when we're doing these subintervals, we can use the left endpoint, the midpoint, or the right endpoint. The previous question told us to use the right endpoint. I'm thinking that when it says this theorem, it might tell us which endpoint to use. It doesn't tell us which. I need to know which endpoint. I'm going to do this based on the right endpoint for right now. If it's not the right endpoint, we'll just come back and adjust it. But if we do this based on the right endpoint, so 0 plus 2 over n, so I think it would just be 2i over n, right? 2i over n, right? So the first one was just going to be 2 over n, and then we got 4 over n, and then 6 over n, so on and so on and so on, based on whatever your I is, okay? So evaluate 5x at the ith endpoint. So then if each x sub I is 2i over n, we want to evaluate f of xi. So basically we plug in that 2i over n into the function. So it's going to be 10i over n, all right? 5 times 2 times I divided by n, okay? Evaluate. So I think in order to evaluate, they want us to do the limit. I think it's similar to the previous. It should be what? The limit as n goes to infinity of the sum. Let me see. If I mimic what we had in the previous, right? If I mimic what we had in the previous, it would be the limit as n goes to infinity of the sum as I goes from where? 1 to n of 5x. Okay. We would have to do, we got to do our f of xi times our delta x, right? So I'll make a note here. It's going to be f of x sub I times our delta x, okay? That will go to 0. The delta x's are 2 over n. I don't know. I kind of feel like I need to click on what this theorem is, but again, that's a link that I don't have access to right now. That all collapses to 0. Evaluate the integral. Okay, the sum, okay? So, for instance, well, we can't really do it. Is there a limit? When I is 1, right? I mean, I know what the integral should be because it should be like, what, x squared over 2. So 5x squared over 2 as x goes from 0 to 2. Okay. So this last part, I'm just going to evaluate the integral. I need to see what that theorem says. Maybe I can look it up. But if I just evaluate the integral, let me see. That would be what? 5x squared over 2 as x goes from 0 to 2. Something should converge. Anyway. 2 squared is a 4, so that's 20 over 2 minus 0, which is 10. Okay, let me think. That goes to 0. What about that goes to 1? Yeah, I think I'm going to look up in the text to see what this theorem is, but it looks like the integral basically goes to 10. So there's a little gap between, and again, I'm trying to apply like what we did in the previous example where, you know, we're basically just doing our f of x i's times our delta x. So that's going to be this guy times this guy for each one, right? But I need to see, there's a little bit more that I need to see. I feel confident about those answers, but I know the explanation is a little bit off. But yeah, so there is a little bit more there. I need to dig. Let me look in the book. I'm going to go with this for now. Maybe at the start of question 5, I'll like come back and try to clean this one up some. Okay, so we'll be back in just a moment, and take care. Peace. All right, so we're back. So all right, so I kind of looked this one up. Let's kind of try to fill in some parts here. So I feel like this is good. The width of each subinterval, all right, 0 to 2 over n. I feel like that's good. Find the ith endpoint in terms of n. Again, I just did the right endpoint, so it was like 0 plus 2i over n. So I think that's fine. Evaluate f of x at the ith endpoint. So f of x was 5 times x. So then I said 5 times the 2i over n. Okay, I feel like that's fine. And then for evaluate, right? This limit as n goes to infinity of the sum as I goes from 1 to n of f of xi times delta x. So the f of xi's, right, is the 10i over n. And the delta x are 2 over n, right? Let me think. So it looks like if we said the 10i over n times the 2 over n, let me see, it looks like we're going to have the limit as n goes to infinity. Now those n terms we can kind of move out to the front. So it's like an n squared. Let me think. 20 is 20i over n squared. over n squared. So that 20 over n squared, I'm going to move to the front. We're going to evaluate the sum as I goes from 1 to n. And I think only thing that's left is the I. So again, we had 20i over n squared. We factored out that 20 over n squared, right? So then in the text, I saw something that says properties of summations, right? If we have the sum as I goes from 1 to n of I, so then this is going to be equal to the limit as n goes to infinity. I'm going to still leave this 20 over n squared. Okay. Now that sum as I goes from 1 to n of I, that can be rewritten as n times n plus 1 over 2, right? So in the textbook, do I have my page number? Jump to, I think this is page 390. I think this is page 390. There's a chart that says property of sums, right? So we got our sum to be in this position. That's where, so we got it in this position. That's where this guy came from, right? So in the textbook on page 390, it says that if you're evaluating a sum that has that form, it can be rewritten in this form over on the right. All right. Yeah, that's fine. Where is it? Let's go back. Right there. Yeah, right. So now, okay, so now let's keep going. So with that piece of information, we still have the limit as n goes to infinity. If I expand the top, we're going to have 20 times, it's going to be what? N squared plus n over 2n squared. Okay. So this can turn this into a 10. Okay, it's coming together. Okay, let's keep going. The limit as n goes to infinity, that's going to be 10 times 1 plus 1 over n. Yay! Yeah, so I was definitely missing that. Like, I don't think I've ever done it that way. That's why I was like, that's why I appreciate this kind of stuff, right? And so we're pretty much there, all right? Let me finish this out, right? So now we can take the limit as n goes to infinity. The limit as n goes to infinity. This guy goes to 0, and we finish with our desired result of 10. Whoop, 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 whoop. I felt like the wildebeest in the Lion King. Whoop, 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 whoop. Right? And that's what we had. I knew the answer was 10. The connection that I was missing, I'll highlight it in orange, was this guy here from the text. Once we got this, you can rewrite that as this guy here. That was the piece that was like tripping me up, right? That was fun. So yeah, but once we got that, then we were able to kind of condense it, take the limit, and we got our desired result of 10. So I don't think the previous one asked us to evaluate, right? So I think that's the completed portion of the fourth question, all right? Let's do a recap. I kind of want to do a recap on that. Just real quick. We'll try to do a quick highlight, quick recap before we move on to question 5, right? So use the form of the definition to evaluate the integral. Find the width of each subinterval. So from 0 to 2, we said 2 minus 0 divided by n. That's where this guy came from. Okay. Find the ith endpoint. So if we start from the far left, we're starting at 0. We're adding each subinterval. So we're adding 2n. We said 0 plus 2n times I. That's where this guy came from. All right. So for the first subinterval, it's just 0 plus 2 over n. For the second subinterval, is 0 plus 2 over n times 2. All right. So on and so on and so on. Evaluate this. Evaluate f of x equals 5 times x. So basically, I plugged this in for x. So I said 5 times this. That's where this guy came from. Okay. So then from there, the final part is we're saying the limit as n goes to infinity of the sum as I goes from 1 to n of f of x times delta x, right? This is what we're doing. When we were doing those Riemann sums, but, you know, it was a smaller case of this. So then this f of xi comes from here, all right? So the 10I over n times delta x, which comes from here, all right? So let me put that intermediate step in there. I'm just being a little bit lazy. Limit as n goes to infinity, because this is what I didn't really feel like writing. The sum as I goes from 1 to n of my f of xi was that 10I over n times my delta x was 2 over n. All right, so that part in purple was the part that I skipped. You know, and then from there, 10 times 2 gave me my 20. N times n gave me n squared. And I basically used algebra. I factored out my constant and my n to the left side of the summation, and I left my I on the right hand side. So then once we had that part in orange, there, that this part came directly from the text, right? Once we get the part in orange, and they have like about 4 different forms. They have like the sum of I, the sum of I squared, the sum of I cubed, and I think there might be or if you have the sum of a constant, all right? So it's 4 different forms, and once you can get it to one of those forms, then you can translate it to this, right? And then from here, now it's algebra, you expand with your ends, you do your cancellations. And then from here, once we got it down to here, when we take the limit as n goes to infinity, that allowed this guy here in blue to go to 0, and we finished with our desired result of 10. Man, that was an adventure. Again, that part in orange, I had never done it that way before. At least not consciously. Maybe I did and I forgot about it. This is like the backstory. Again, just do your best with like these Riemann sums. You know, we can work some more examples if we need to. But honestly, I feel like it gets easier going forward. Let's go ahead and move into question number 5. All right, question 5. Okay. So then our question 5 in our series of 8. So it says the graph of f is shown. Evaluate each integral by interpreting it in terms of its area, right? So first they want the integral as x goes from 0 to 10 of this function. So basically, what's the area on the curve? So we can break this into like its simple shapes, right? If we think in terms of its simple shapes. So like for instance, if we just want the area from 0 to 10, right? That's 10, that height, what's that height there? 15, right? So like for instance, if this is 5, this is 10, this is 10, right? Okay. So then length times width. So for that rectangle, it's what, 50 plus 1/2 the base times the height, so plus another 50. So from 0 to 10, it looks like the area under the curve is 100 square units. All right. If you break it into the simple shapes, it's a rectangle with an isosceles right triangle. The area for a triangle is 1/2 the base times the height. Area for a rectangle is length times width. So then those two pieces together, I got 100 square units for the area as x goes from 0 to 10 for that first part, okay? 0 to 25, okay? So again, let's do our simple shapes. I'm gonna get rid of my notes here. Okay, so if we do our simple shapes, okay. So we have a triangle here. We got a shape over there. We just did 0 to 10. Okay, so we know that this region here is 100, provided our calculation is proper. 10 times 5 is 50. Yeah, 100, right? So from the previous, we know that this area should be 100. And the middle looks like we have a rectangle. So the length times the width, that height is 15 times a width of 5. So 15 times 5 is 50 plus 25 is 75. So I'm getting that area to be 75. Oh. And then the last one is a right triangle. So 1/2 the base times the height. We'll use green. So 1/2. The base is going from 15 to 25, so the base is 10, and the height is 15. So 5 times 15 is 50, so 75. So it looks like the area of that region is 100 plus 75 plus 75. Okay. 140, 150, 250 square units. Okay. Let's keep going. So now it asks us to find the area under the curve as x goes from 25 to 35. Okay. let me get rid of my notes here, 25 to 35. So 25 to 35, so just like this region. All right, looks, this simple shape looks like a right triangle. 1/2 the base times the height, so 1/2. The base, that distance is 10. That height, 5, 10 is 15. So 5 times 50, 75. So for this one I did 1/2 10 times 15 to get 75. Square units, okay? 15 to 35. Okay. So I think they cancel each other out, right? Because 15 to 25, right? When we did, right? 15 to 25 looks like it's 75. And then 25 to 35 is also 75. And I think we got to subtract those, right? So we would say 75 minus 75 to give us 0. I'm definitely going to need you to check these just to make sure. But I got 0 there. Okay. The absolute value. Okay, so now instead of that part being negative, instead of saying 75 minus 75, now we would say 75 plus 75 for that next part, because it's the absolute value. Want to duplicate. Get rid of that. That needs to say plus. 140, so that's 150 square units. Yeah, because it's like when it goes above the x-axis and below the x-axis. When it's above the x-axis, it's considered positive. When it's below the x-axis, it's considered negative. So you got to say, you know, the top minus the bottom, right? Duplicate. So that's, at least when I looked it up, that's what it was. Okay. 0 to 10. What's the difference? Didn't we do this one already? Oh, okay. Oh, shiesta. So we did 0 to 10. Now we're doing from 10 to 0. So I would imagine it would be negative of that. I would say negative 100. Okay. So again, just try these out. Let me know if these do or don't work. If they don't work, then obviously we have to come back and clean them up. All right. So with that, we're going to go ahead and end the session here, and we'll be back momentarily for the next few installments. Take care, and from one beautiful mind to another, take care and peace. All right. Greetings, YouTube. Beautiful Mind here. We're back with the 6th and 7th installment of the series of 8 from these questions from calculus. Let me see. I feel like these, unless I'm not looking at it properly, this first one asks us to find the integral as x goes from 2 to 2, right? When we evaluate that definite integral, whatever answer we get, we're going to say that answer minus that answer, right? The area under the curve is practically 0, right? Because it's going to be something minus itself. So that one, I would imagine that result should just be 0. Right? And then for this, the 7th question, it says that if the integral as x goes from 1 to 5 of this function is 9.2, and the integral as x goes from 4 to 5 of this function is 5.6, we want to find the integral as x goes from 1 to 4. So the area under the curve as x goes from 1 to 5 is 9.2. The area under the curve as x goes from 4 to 5 is 5.6. So then if we want the area under the curve as x goes from 1 to 4, we just say 9.2 minus 5.6, right? If that were 6, that would be what? 3.2. So then 3.6. So I'm getting like a 3.6 there. And again, for that 3.6, for that one, I just did the 9.2 minus the 5.6. And so what was the area left over was 3.6. Okay, so that's about the best I can do there. We got one more question left, so we'll be back in just a moment. With that, we're going to go ahead and end the session here. From one beautiful mind to another. See you in just a moment. Take care. All right, and we're back. Beautiful mind here with the final installment of this series of 8 questions from calculus. This question says, let's see, if lowercase m is less than or equal to f of x, which is less than or equal to capital M, for all a that is less than or equal to x, less than or equal to b, where lowercase m is the absolute minimum and uppercase m is the absolute maximum of the function on the closed interval from a to b, then we have this property lowercase m times b minus a is less than or equal to the integral as x goes from a to b of f of x dx, which is less than or equal to capital M times b minus a. Use this property to estimate the value of the integral. So it seems like a squeeze theorem. So at first glance, I was thinking, okay, well, let's find the absolute max and the absolute min of this function. That would entail taking the derivative, finding the critical values, and then using the endpoints of 0 and 4 to find the absolute max and the absolute min. So let's do that, and then see where it goes from there. Okay. So we have this f of x equals 3x e to the negative x. Okay. Let's take the derivative here and let's find the absolute max, absolute min. So then f prime, looks like we have to use the product rule. First times the derivative of the second, plus the second times the derivative of the first. So the first is this guy. The derivative of e is itself times the derivative of the power, so times the negative 1. So that's the first times the derivative of the second, plus the second times the derivative of the first is this. Okay? It looks like we can factor out 3e to the negative x from both terms. So we can factor out a 3e to the negative x, and then what's left over, 1 minus x. Okay, so the critical numbers are going to be those values of x that makes this guy either 0 or undefined. Now with that first factor, that's 1 over e to the x. So if we just consider e to the x, right? E to the x lies entirely above the x-axis, so we can't find an x that's going to make that y value 0. And then when we replace x with negative x, that flips the graph horizontally, so we have exponential decay, which still lies entirely above the x-axis. So this guy, we can't find a 0 there that's going to make that, we can't find an x that's going to make that 0. But from the second factor here, when x is 1, right? So when x equals 1, that's our critical number that we want to test, because it's going to collapse everything to 0, right? Okay. So then, I guess if we just want absolute max and absolute min, we just need to test this guy with the endpoints, with 0 and 4. We should verify whether it's a local max or a local min. Let me stop being lazy and just do that. I'm trying to skip steps. All right. So here's my positive x. Here's 1. We want to compare this in f prime. This is going to give us a 0 in the derivative. A number on the left to test inside the derivative is like when x is 0. If we test x equal to 0, this guy is positive. This guy is positive, right? So this ultimately is positive, which means the original is increasing left of 1. A number on the right of 1 to test is when x is 2. This guy's going to be negative. This guy's going to be positive. Positive times a negative is negative, which implies the original function is decreasing. So this should be a local max. This is a local max. But we still need to compare it to the endpoints to find the absolute max and min. So we have our, I guess I'll just work down here. X times, or compared to f of x. I think our endpoints are 0 and 4, and we need to test 1. So 0, 1, and 4 into the original. Okay, so I'm going to use my trusted dusty Rusty. This guy. Okay. I really want to work some more of the other ones that I struggled with in those previous questions. Just to kind of polish it, because I know the presentation was a little bit shaky. But I feel like by the end of it, we kind of got to the meat and potatoes of it. We were able to resolve it by the end, right? So as long as you can kind of make it to the end, step back for a bit and process it, I think it's gettable, right? So anyway, let's go to our y equals. We got 3x times e to the power of negative x, okay? And what we want to do is evaluate this function at these 3 values. I guess I could just do my table. So if I go to table set, I want the table to start at 0 and change by 1. I'll hop over to the table. Okay. So when x was 0, we got a corresponding y of 0. When x was 1, we got this, let's see, 1 over, so 3 over e. It should be 3 over e, which is approximately 1.1036. And then when x is 4, 12 over e to the power of 4. $21,979. $10.36. 1.1036. Okay. Okay. Let me kind of check and make sure those are proper. 3 over e. 1 point, okay. 12 divided by e to the power of 4. 21,979, 21,979, okay. So then the absolute max, we get this for a max. See, now that's funny. Even though, okay, it was a local max and it just turned out to be our absolute max on the closed interval from 0 to 4. And our minimum value was here. The absolute min was here. Okay? So we have our max and our min. So it says lowercase m is the absolute minimum. Smaller value. Okay, so if our absolute, wait a minute. B minus A, so it would be 4 minus 0 times 0. So the smaller value is 0. And then the absolute max we got was at 3 over E. So 4 minus 0 times 3 over e. So 4 times 3 is 12. 12 over e. So where our claim is that the integral of this function from 0 to 4 is somewhere between 0 and 12 over e. Over e to the 4. Wait a minute, I gotta back up. No, 3 over e, yeah, we're good. 3 over e times 4 is 12 over e. So our claim is that this integral, the integral of this function as x goes from 0 to 4 is somewhere between 0 and 12 over e. Okay, I mean, yeah, all I did, I found my minimum, I evaluated this for the smaller value, I found my max, evaluated this, that's how I generated those numbers. All right, so that's, again, just check it, let me know if it does or does not work, and, you know, we'll work it out if it doesn't work. Okay. And so that concludes. I know it got a little bit dicey, but again, I left the raw edits just because I feel like that, you know, that struggle still needs to be there. Like, you know, people just need to be aware. You have to struggle. You just kind of push through it, reference, dig, you try, you research, you like when I pull up the book showed me this property of like, you know, summations, which I had never used before like that. I think when I teach calculus, I'm teaching business calculus, so we just kind of get into like calculations instead of, I mean, and we have some applications, like some real world applications, but we don't get into like the nitty gritty and the nuances. Like we don't really use like any pre-cal like that, and we don't go so in depth on like the Riemann sums. Like we'll introduce it, but then we just get into like the differentiation and integration techniques. Like we kind of bypass a lot of that stuff. But anyway, but it's still there, and so I think, like I said, I feel like we got to the bottom of it, and I feel like there's something that you can pull from it. I know it's not; it could be a little bit daunting or deterring or whatever, but anyway. So with that, we're going to go ahead and end the session here, and now from one beautiful mind to another, take care. Peace.